It's 8 o'clock, so we'll go ahead and get started. Thank you for joining us early on this Wednesday morning. Welcome to our special panel session on bringing space down to Earth, space physics in the laboratory. I'm Amy Kesey. I'm at West Virginia University, and my co-chair is Greg Howes from University of Iowa. Just to give you an idea of how we're going to run the panel, I'm going to give a quick intro to the topic and what we've been doing this year on this topic. And then each of the panelists is going to have a chance to give a brief introductory talk to their relationship to the topic and some of their ideas on some of the questions we've given them. And they'll basically talk for 8 minutes and then have a chance for questions from the audience to the individual panelists. And then at the end, we'll have a 30-minute open discussion, and that way we can ask questions of the full panel. So to give a little background, this all started out in the spring when Greg hosted a workshop at UCLA that brought together space physicists and laboratory plasma physicists to start talking about how could we work together on the same topics and really make some progress. And then that was followed up at the APS Division of Plasma Physics meeting in October. There was a mini conference on this topic, and Greg also gave a plenary talk. So we really introduced the topic to the laboratory plasma community to make them aware of some of the big questions that are going on in space physics and how that they can help. And now we are here at AGU, so we can really get the space physicists talking about what can the laboratory plasma people do to help out. And so those are our big goals for this groups. So just want to talk about some of the big questions that are being asked in space physics, from solar dynamics, thinking about the solar dynamo, flares and coronal mass ejections, and then on to geospace dynamics, looking at geomagnetic storms and substorms, understanding the Aurora, and looking at the effects of space weather on our technology. Looking into the outer heliosphere, understanding the termination shock and the interaction with the interstellar medium. And then looking further out into planetary dynamics, understanding planet formation, the magnetospheres of the outer planets, and even astrobiology. So we have lots of big questions in our fields. So how can laboratory measurements help us answer these big questions? Well, laboratory experiments have several advantages. A lot of times when you are looking at satellite-based missions, you have single point, or even with the multi-spacecraft mission, just a few points. But when you get into a laboratory, you're not limited to that. You can take many more measurements across the space. The experiments are often reproducible, so you can take many measurements and build up your statistics. You have some control over the conditions of the laboratory experiment, so you can have a better idea of having a control and really understanding when you vary certain parameters, which ones are having the big effects on the phenomena that you're studying. They're also lower cost than spacecraft missions, so orders of magnitude, even when you build some of these big laboratory experiments that take up really big rooms, they're still cheaper than launching into space. So how should we utilize these laboratory experiments? So first of all, we can study fundamental physics processes. So if we're looking at something like reconnection and trying to understand how that works on the sun or in the magnetosphere, we can do reconnection in the lab and really get an idea of what's going on with that. We can also help interpret measurements from spacecraft. So if your spacecraft flies through something and takes a measurement, you don't know what's going on, you can try to reproduce it in the lab and get a better handle on what's going on. It also can help guide mission design and analysis, so you can do some experiments in the lab before you get out into space, and so you can test out different ways of doing it, or once you've got it up there, you can try your analysis method on some laboratory measurements and then use it on your spacecraft data. You can also use it to test new diagnostic capabilities. So NASA usually is very low risk with diagnostics, and they want to see something that they know is going to work before they launch it, and so you can try it out in the lab and show that it really works before you try to put it onto a NASA mission. So these are our overarching goals for the panel session, so I want you to keep these in mind as you listen to what the panelists say, and hopefully we can hear it over the train, as well as think about the questions that you want to ask the panelists as we go into our discussion. So like I said, the goal of being here at AGU is to really get the space physics community to understand what is going on in the laboratory right now and how they can be used to inform each other of the different experiments. We also want the space physics community to really come up with the key questions that the laboratory people can help out with. So what are the big questions that you're working on, and what key measurements can the laboratory physicists do in order to help you out? And then really work together. So we'll talk about, we can talk about some of the future facilities and diagnostics that are coming up, and how can we work together and help out the space physics community with those new things that are coming up. And I think that is, yeah, that's the last. So I'm just going to leave the goals up for a minute so you can look at those, because I'm running a little bit ahead of time. But what we're going to do is we're going to start at the far end and work this way on our panelists. All right, so our first panelist is going to be Craig Kletzing. So he is on this one. Yeah, all right, so the keyboard's right here.
There we go.
This mouse is this one.
Kill that, and then go back one, I think. Yeah, there you go. That's it. All right, excellent. And Control L. There we go.
All right, set this guy.
Well, good morning, everybody. I've actually been involved doing both space and lab experiments for quite some time. So what I thought I'd do is tell you a little how I got into this. So my initial motivation was the Aurora Borealis. For many, many years, this was my primary area of research, doing sounding rocket flights and working from satellite data. And so back in 1994, I published this paper. And this was showing what an Alfvén wave can do. And what you see in the various panels here is this was going from just before the Alfvén wave arrives to after, where the Alfvén wave has gone beyond. You see sort of two things going on there. One is the bulk of the plasma, the distribution actually moves in one direction and then back. This is electron distributions that we're drawing here. So these are phase space density plots, logarithmic scale. And so what you see is that motion of the core of the distribution sort of down and then back up. And what this is the slosh, if you will, of the electrons in the Alfvén wave that carry the parallel current in these waves. This is an inertial Alfvén wave. And the part that was really quite interesting was this little bit you see in the very first panel, which is actually before the Alfvén wave arrives. This small group of electrons that are running ahead of the Alfvén wave and are at about twice the Alfvén speed. And so this is resonant acceleration. And you can work out the theory, and we published this, but like many space plasma things, trying to prove this definitively with spacecraft data is a pretty tricky thing to do. So I had this great idea of I would go to this meeting I had read about called the Interrelationship of Plasma Experiments in Laboratory in Space, or IPELS. And so I went to this meeting in 1995, and there was this guy, Walter Geckelman, and his student at the time, David Linneman, and I tracked them down and said, hey, come look at this. I said, you guys should do this experiment. And, they kind of, nodded their heads a little, and so, nothing happened. So the meeting happens every 2 years. So in 1997, I went and had worked out all the theory, because I knew they had a cylindrical device to do Alfvén waves with a Bessel function exciter and all this, working everything out in cylindrical coordinates, and showed this to Walter. David, I don't think, was at that meeting. And, Walter kind of nodded his head, and I said, well, look, could I propose to do this experiment if you guys don't want to do it? And he said, sure, go right ahead. So I wrote this proposal to NSF, and much to my surprise, we got funded. And so I met with George and George Morales, and we talked about this. And George said, well, your Bessel function exciter, you're essentially assuming you have an infinite plasma in all directions. So why don't you just use an orthogonal system to do this? Because if you're going to make that assumption, it's a lot easier to work in Cartesian coordinates. And so we came up with this antenna, which maybe you can see. This is actually a picture inside the large plasma device, or the LAPD at UCLA. And you can see our antenna consists of these little grids. It's a small thing there at the center in the vertical direction. And this actually was a few years in of working out to build this kind of particular exciter, which would allow us to actually tailor the wave spectrum in the perpendicular direction. So we could essentially treat the vertical as being infinite, and then we could bias these various grids and to different amounts so that we could produce whatever K spectrum in that direction we wanted. And so it took us a fair bit of learning, actually. You know, when I first proposed this thing, I thought, you know, we'll do these experiments. You know, the first year we'll work out a few bugs, we'll make all the key measurements, and you know, the next year or so we'll publish the PRL that we've seen resonant acceleration, and we'll be done after 3 years. It didn't quite work out that way. And so we eventually built up this system so we could launch Alfvén waves with a tailored K spectrum. And what we got out of that was the ability to actually verify that the inertial Alfvén dispersion relation was correct. Because one of the interesting things was, although there had been some experiments that had been done that had looked at that sort of in a broad context, and particularly what the Geckelman's group had done this. They'd used disk exciters, which produced a wide spectrum and makes a cone of Alfvén waves, but to actually carefully go along for each perpendicular K value and measure it was something that we sort of got sidetracked onto doing, and there were various things along the way. We developed the antenna where we could bias all these grids. We had to develop our own diagnostics because we had very, the waves were not particularly strong, so we needed very sensitive measurements. That was an interesting thing, learning how much heat can be transported by a plasma. Because you don't think about that when you put a probe into a vacuum vessel, that you better be careful about how hot it can get. So we cooked our electronics the first couple of runs we tried. And so we were able to actually verify this dispersion relation. I just put a couple of these on here. Here's at one frequency and another frequency. These are both, and the line down the middle is basically the theoretical prediction with error. We put the error bars on that because it's easier to plot the various points of where they came in. And so this turned out to be kind of a nice result after several years of working out various things that we were doing wrong and learning how to do it. So one of my points is that I'll bring up when I conclude is that the way this worked best for us was we were actually going out there, we were helping, we were mostly doing the experiments ourselves. In fact, when we first started out, it was not even a user facility. And back in those days, it actually let us put stuff on the device ourselves and pump things down. They've gotten a little touchier about that because if you screwed up for all the other users, they get a little upset with that. So, but we still work with them closely. Since then, we've kind of gone on over the years, and so this sort of evolved into a different set of experiments where, in collaboration with Greg Howes here, we got interested in trying to understand some of the basic fundamental theory of plasma turbulence. And one of the basic things is this wave-wave kind of interaction and being able to see, can you actually verify that in a lab? I mean, one of the things that I found in all of this work very interesting is there's a lot of theory that we use in space plasma where we assume that the core theory is actually correct, but detailed experiments that verify that theory are relatively few, such as it was with the Alfvén waves. I mean, we've been doing inertial Alfvén waves theoretically since back in the late 70s with people like Hasegawa and so forth, but to actually carefully measure that in the lab is something that really hadn't been done until, about, less than 10 years ago now. And so this was a beautiful example of wave-wave interactions. So what we're doing is showing in the upper right panel there is one antenna. It's a big antenna that UCLA has, launching a wave at a certain frequency that produces the K spectrum that you can see here. And then in the lower left-hand corner is our antenna launching another wave towards that wave, except that it's launched in it's on a different axis. So you have these two, a KX and a KY, and as a little diagram in the upper left shows, what you get in the lower right is, and that's actually, these are other than the upper left corner, those are all measurements, is you actually get the expected, K plus K adding of the wave. And this was really nice. Greg had predicted how we ought to do this experiment from gyrokinetics model, and so we went ahead and did it. And we were very excited because lots of people have been trying to get this to happen for quite a while. And it actually turned out that it took this coupling of theory, us doing experiments in the laboratory, and putting this together to actually show this effect with some very interesting results about exactly when you can get this kind of thing at a high enough order that you could measure it in the lab. And then this is some of our most recent work. So we've kind of returned back to trying to understand Alfvén waves. And we developed a diagnostic, and again, this is another collaboration with another colleague at the University of Iowa, a guy named Fred Skiff, who is sort of a master of plasma diagnostics. And This is actually using something we call our Whistler wave diagnostic, which uses the electron cyclotron resonance to you sort of sweep through that, and the particles at a given speed are resonant due to the Doppler shift and are absorbed. And so from this you can derive the reduced parallel distribution function. And what you're seeing along the vertical axis here is phase relative to the wave from 0 to 2 pi. And then the two halves of the two different directions, the left-hand side being basically in the direction that the wave is launched. And what this is showing quite clearly, and I just picked one slide because I didn't want to get into a lot of detail here, is that this is actually showing that electron slosh. That is what I showed in my second slide of the whole distribution moving in one direction and then back again. And this is showing that indeed what we see is the whole core of the distribution moving in response to the wave field, just as expected by theory. And so we continue this. We've actually just developed a new antenna in the last couple of years, and our hope is in the next year or two to finally have a big enough amplitude alphane wave that we can actually see the resonant acceleration and demonstrate that some of the theoretical models we've been using for quite a long time actually hold up. So with that, I'll conclude with various things. I think, one of my key points is that if you're interested in this stuff, you really got to get involved with the lab guys. You can't just sort of toss it over the transom and expect them to do things because they have their own views of how stuff work, and they've got their own set of laboratory experiments that they're interested in. So if you have an idea, really the thing to do is to track down some of the lab folks and wrestle them to the ground and say, look, I'd like to do some experiments with you. What do we have to do to get there? Another thing is I really recommend, if you're interested in this, is going to the IPELS meeting. It's held every 2 years. I forget exactly where the next one is. I think there's some proposals floating around. But this is a meeting where a lot of lab folks, particularly those that are interested in doing collaboratory experiments with space people, show up. And so if you go to one of these meetings, you can track people down. I enjoy them quite a bit too, because there's a very heavy emphasis on plasma physics at these meetings. So it's kind of healthy to keep yourself reminded of some of the details of things that people worry about, because we have so much morphology in space physics that you sometimes lose some of the fine details. And so that's what I quite strongly recommend. And persevere. Sometimes experiments take a little bit longer than you expect, because laboratory plasmas are not as easy to work with as you might have hoped they were. They still, as Amy was saying, are reproducible, and you have the opportunity to change parameters and really test a theory out. And you can make these very comprehensive measurements. What I was showing you before, often these whole planes of measurements. So you can really watch wave propagation and things like that in quite a bit of detail. So I'll stop there.
All right, we have time for questions.
So, Greg, you mentioned about IPELS. So indeed, I agree with you. At the same time, at least the IPELS has been a very important platform for the discussion between space scientists and others. And indeed, Greg experiment was a very important feedback on the IPELS.
Well, I think that just goes to my point that the most effective way to do this is to directly get involved yourself. You may not necessarily be operating the experiment, but if you have your idea, meet the lab folks, but actually work with them on things. You can't just sort of stand off to the side and expect things to happen. And I think that's the way, actually it's more fun that way too, because you really understand all the things that are going on. And I think it's the effective way to do this. And the IPELS, well, it goes way back. I mean, it's been for more than 20 years now, and I think it's a very effective way to both meet people, but also to get ideas and interact.
By the way, next meeting will be in Japan.
Oh, it's in Japan, okay.
2019.
Right, so not this summer, but think about it for the next summer, because it's a great meeting to go to. It's small enough that you can really talk with folks, and so I think many of you would find it a very refreshing meeting to visit.
All right, thank you. Our next speaker is Bill Amatucci from the Naval Research Laboratory, and his talk is a laboratory simulation of space plasma physics phenomena. Thank you.
Well, if I had seen Craig's abstract before I submitted mine, I probably would have titled this "A Laboratory Experimentalist Goes to Space," because I'm going to tell you in a few slides how some of the diagnostics that we've developed in the lab, we're now actually flying in space and getting our own space data. But the bulk of our work is done in the laboratory, and this is the space physics simulation chamber at the Naval Research Lab. This is a large-scale plasma device. It's 2 meters in diameter, 5 meters long, so you can stand up inside of it in the main part of the chamber. And then there's an additional part extended to the front here, which is another 2 meters in length and 0.5 meter in diameter, called the source chamber. These two chambers can operate in tandem, giving you 7 meters of plasma column length, or they can be isolated by a valve, and you can actually run 2 different experiments simultaneously in each chamber. We have a variety of plasma sources. You see one glowing there to the right. And we can control the plasma conditions, as Amy was mentioning, so we can scale them to different regions. And you see there are magnetic field coils surrounding the chamber, which is used for confinement of the plasma, but they're also individually controllable, so we can shape the magnetic field to meet different geometries that might be relevant in different regions of space. So here's an example of a few of the plasma sources that we use. In the upper left is a microwave discharge plasma source. Maybe Kristina will talk a little bit more about that during her talk, I don't know, because she uses one as well. And then a helicon discharge source and a large area hot filament source. And so using these various sources for whichever particular needs we have for an experiment, we can dial in conditions that map to certain phenomena that we want to study. We can also do more exotic things in there. We do a lot of work at the Naval Research Lab recently on investigation of the dynamics of the radiation belts. And so here we're making a little slice of the radiation belt in the plasma with various electron beam sources, which we can put in at controllable energy and pitch angle with respect to the field, and then look at, for example, we look at a lot at the interaction between Whistler waves and the radiation belt particles, looking at wave-particle interactions and some of the nonlinear effects there. So we can control those conditions quite precisely, the various pitch angle and energy, and really diagnose the effect in great detail. We have a wide variety of diagnostics that we use to study this, and we also want to take advantage of the full 3D volume of the chamber to investigate the spatial characteristics of these plasma phenomena. So we have 2 internal positioning systems that span the length of the chamber and also the full 3-dimensional characteristics. So we can position probes wherever we want and control them and really get high spatial and temporal resolution of the phenomena that we want to study. Now here's a plot taken out of one of NRL's famous contributions to plasma physics, the plasma formulary. This shows a wide variety of plasmas and where they fall in this particular space, where we have the temperature of the plasma plotted on the horizontal axis and density on the vertical axis. And you see that space plasmas tend to lie over in the kind of lower left corner, and the NRL space chamber can make conditions that cover a wide variety of those ranges. But what's important for doing laboratory investigations of space plasmas is not that you match the absolute value of the density or the temperature, but if you want to get at the core of the physics, you really have to match the important dimensionless parameters that control the physics of the phenomena that you want to study. So you have to understand what it is that you're looking at, and then dial in the conditions that you need to do a credible representation of a space plasma. So when you do that, here's an example of, well, I don't know why it's so hesitant there, but this is an example of a lower hybrid wave propagating in the plasma. This is part of our radiation belt dynamics studies, and you can see that in the laboratory, you can create the conditions, create the equilibrium that you want, launch the type of wave that you want to see, and then have that in repeatable fashion so that you can go in and diagnose it to death with whatever diagnostic you want and get a real representation of the wave field. And this is an excellent complement to space physics, where of course it's very important to study space physics in space because you need to know what's going on and what those equilibrium conditions that you're shooting for. But you only get a snapshot of a particular phenomena. And we can take those conditions that you find, recreate it in the lab, and recreate it time and time again, and investigate these phenomena. I mentioned that we also do a lot of diagnostic development in the chamber. This is one example of a plasma impedance probe that we've been working on. Got our start in this with our friends from Utah State University. Chuck Swenson got us going on this, and this has been a real boon for us. We use this as a laboratory diagnostic and find that it also has a lot of value in space. So this is looking at the AC impedance of a plasma, and you sweep the frequency and you get the spectral AC impedance spectral characteristics, and you can infer a lot about the plasma. We've flown this on the CARE-2 sounding rocket. This is an NRL sounding rocket flown by Paul Bernhardt, and you can see a picture of the probe there. And we also are going to be flying this on NRL's TEPSI CubeSat, and the biggest mission that we're doing, we're developing the probe right now for, is the STP-H6 mission to the space station, where we'll get at least a year on orbit to look at how this probe works. Finally, another great thing about having a large chamber and a large volume plasma that you can dial in space conditions is that you can test space instruments before you fly them. Amy was mentioning this. It's a great platform for qualifying an instrument before you fly it to buy down the risk. Here's an example where, again, with our friends from Utah State, this is the floating potential measurement unit, which was going to the space station. And we tested it in the chamber and fully plasma qualified it before they flew it, and there you can see it in the upper part of the picture on the space station. So what I hope I've gotten the point across to you is that laboratory experiments can be a very good complement to in situ space physics. Not only is it cost effective, but it can be used as a powerful tool to help understand and interpret space data. We have the flexibility to create conditions over, wide ranges, and we have a lot of diagnostics to really get at the essence of the physics that you're trying to see. And we can be an important player in that there are often theoretical models developed to understand and interpret space data, and we can play a major role in validating those theories so that they can be applied with greater confidence to the space data. As I told you, there are three main ways that we use the space chamber for the study of fundamental plasma processes, waves and instabilities, development and testing of plasma diagnostics, and pre-flight qualification. So just some examples of other things besides the lower hybrid waves that I showed you. We have an extensive history of studying inhomogeneity-driven plasma instabilities, looking at auroral ionospheric heating and outflow, magnetospheric boundary layer dynamics, and then nonlinear Whistler wave effects and how that affects behavior of the radiation belts, along with our testing and qualification of space instruments. So with that, I'd be happy to take any questions.
Thank you. Can you specify the density of the neutrons and how that will affect the experiment in general?
That's an excellent question. Yes, so you have to have neutrals in the plasma to create the plasma, and the neutral pressure is higher in the chamber than it would be in the space conditions. We do have some control over that. We can, depending on the various plasma sources that you use, you can control how many neutrals you put in there. But one of the important dimensionless parameters that you want to look at for example, studying waves in the plasma is what is your wave frequency to collision frequency ratio. And although the neutral pressure is higher, very often the wave frequencies, when you look at the scale conditions, are higher as well in the chamber. So you can make the waves essentially be, collisionless compared to the, collision frequency. The wave frequency is much higher. So yeah, it's important to look at and be aware of, because that can seriously impact the physics, yes. Rob?
You mentioned something about reproducing equilibrium conditions applied in space, but of course one of the big problems is that there really aren't any equilibrium situations in space. Everything is always dynamic and is always driven and has a lot of multi-scale coupling.
True.
I'm not sure. I mean, obviously you do as well as you can, and you do have a good idea of reproducing the dimensionless parameters, but there's always that caveat that taking the information from the laboratory experiment and applying it to space you have to be careful about that sort of thing.
That's true. There are scales that you can't reproduce in the lab, but for example, these dynamic equilibria, like for example the inhomogeneity-driven plasma instabilities I was mentioned, that's not an equilibrium. We force that equilibrium by driving flows in the inhomogeneous flows in the plasma, et cetera. So we can create those unstable equilibrium and look how they reproduce, and we can look to some degree at the cross-scale couplings, because we have a large volume. If you create conditions where, you're starting off small and it's cascading to larger, yeah. So we do the best we can, but we realize that space physics has to be done in space, right? And sometimes it's a multi-step process to investigate these.
All right, thanks. We have to move on to our next panelist. We will have time for more questions at the end.
Yeah. I do want to emphasize we will have a whole half an hour for discussion and more questions at the end. So I encourage you to stick around and keep those questions in mind. We definitely want to address all of that, but we do want to make sure that we get through, give everybody a chance to give a few minutes of speaking. So I want you to welcome Thomas Moore, who's going to be talking about complementarity of laboratory and space experiments on reconnection.
Thanks. This is kind of personal perspective with reconnection as the focus. And I have to be clear that I've never been in a plasma laboratory except as a voyeur or a tourist. I've always done all my work on space experiments of one form or another, but I have paid attention for the most part, been pretty consumed with the MMS mission for the past decade or so. And so I asked Li Jian Chen to kind of back me up on this, who I know she has been paying a lot more attention than I have to laboratory work, recent laboratory work. There's three things I want to do. I want to just convince you and admit to you that laboratory work on reconnection has been absolutely crucial to building a mission like MMS up over time. Secondly, that I want to brag a little bit about MMS accomplishments, although there's lots of other talks about that you could see in this meeting. And thirdly, I just want to sort of identify things that we wish we could do in space that we think can only be done in an actual laboratory. So let's go ahead to the first chart. I've been around, oh yeah, I'll do it. No, it's the Mac, okay. Yeah, I've been around long enough that I also remember early 80s work by Walter Geckelman and others, and that really was about the same time as the IC results were coming out, perhaps. But back in the 70s, reconnection really was not a fully respectable topic. I mean, there were a lot of skeptics in our field who mounted every effort they could think of to prove that reconnection there were other solutions to what was going on and didn't need reconnection, or that it was just not. They tried to disprove it over and over. There were a lot of people. So just establishing it as a real problem was a significant factor. And my memory of going to AGU meetings and seeing Walter Geckelman's just gorgeous maps of observations of reconnection in the laboratory, there's vivid memory that I have of that. And I think it influenced a whole lot of people, kind of mowed down some of the skepticism about reconnection and showed that it was a real and almost tangible thing that you could do in the laboratory. So this is a more recent example here. I'm going to flip through a few examples without talking too much about them, but identifying the electron diffusion region in the lab so clearly. Another one is, oops, yeah, I can grab the right keyboard here. Showing that asymmetric reconnection can be created in the laboratory and studied. And of course that illustrates the ability of the laboratory to control boundary conditions. Very important, I think, and I'll come back to that. But here we have asymmetric reconnection contrasted with symmetric reconnection in a laboratory situation. Another one, you can generate plasmoids, so you can do some dynamics like we have in the magnetosphere. Bob's point about dynamics being more difficult or more prevalent in space is certainly relevant, but people have been able to show that you do get dynamics, and I need to dig into that because I'm very interested in that topic. But I'm basically just showing you something suggestive there. Now, for MMS, I'm going to switch gears and just brag a little bit on MMS. This is an illustration here of 7.5 millisecond resolution of electron distribution functions and other parameters in the stack plot. But it's, I think, a second of data there with a movie of the distributions being obtained. So we had a huge improvement in measurement speed over previous missions just by virtue of investing a lot in the instrument to do that. We made many things are being clarified and elucidated by MMS, and mostly so far on the day side, but now increasingly on the night side. We've got the 4 spacecraft and payloads that are fully operational, continue to be. With enough fuel now, we've realized those engineers are very conservative about things, and they were a little uncertain about how much fuel we would consume flying formation with the 4 spacecraft. It turns out they were grossly pessimistic, and we find ourselves with 30 years of fuel supply up there now, which is kind of nice. We might have to figure out where else we're going to go in the heliosphere. But let me see if I can get on to the next one. Well, there it goes. Yeah, so this is kind of iconic chart from Jim Birch's work on a particular event, but the point that I want to make is just to illustrate what can be called the engine that drives reconnection, the way that the current gets carried, or the way that the current is retarded in some sense and needs to be driven by an electric field that becomes a reconnection electric field, has to do with these meandering motions of the electrons on electron scale boundary, yielding a dissipation and a reconnection electric field, and also normal electric fields that work on the meandering motion. I won't belabor that point, it's just to brag on the ability of being able to resolve those features for the first time in space. This is a comparison of the kinds of features observed in both the electrons at the upper row and the ions in the lower row, simulations from Wang et al. I think there's a little bit of discussion and argument going on about whether or not the crescent feature in the electrons is truly indicative of agyrotropy. I mean, it looks pretty agyrotropic, certainly. But there are also other features like little pairs of beams seen right at the X-line. So the EDR now, we're able to resolve it and see that it actually contains substructure and interesting features. But returning to complementarity here, I think, from what I'm showing you here, I conclude that space is a place where larger scales are more accessible to sort of more ambitious instruments, or bigger instruments at least, that in principle ought to be able to do more. Makes me wonder, what do you wish you could do in the lab that you so far haven't done, that we could do for you in space, perhaps, in the spirit of complementarity? And then again in the lab, you've got boundary conditions much more accessible to control, which really sort of lights up interest among the space physics folk. We wish that we had, the biggest thing we wish we could do in space is control the circumstances. We call it a laboratory for plasma physics in space, but it's really more like a casino where you, you kind of have to get lucky. And sometimes seems like the house is in charge. But so this is what we wish we could do in a little bit more detail. We'd like to explore how the current sheet width and reconnection rate adapt to boundary conditions. I think we really want to know that. And we'd like to be able to make a diamagnetic current sheet and thicken and thin it at will, and make it go from diamagnetic to non-diamagnetic and dissipate it, for example. We'd like to measure the rate as a function of the boundary conditions, including shear, pressure, beta, alphane speed, all those dimensionless and dimensional quantities that we think influence the rate of reconnection. And, you know, there's this underlying hypothesis that's sort of plagued reconnection from the beginning, which is that, well, is it enabled and controlled by the microscale processes going on at electron scales? Or do those processes somehow sense what the boundary conditions are and adapt themselves to the boundary conditions? It's still hard to address that question, I think, without being able to control the boundary conditions and vary them. So we'd like to know how the dynamics of the current sheet works, thickness of it, what makes it thick or thin, and how it gets thin, clearly down to electron scales, and what the response is. Another aspect, what would be the response of reconnection to a step change in the boundary conditions? So somebody, you know, turns on a source, or a blob arrives in the solar wind and suddenly gets processed. If a step change like that propagates through a reconnection region, what does it do? And in particular, does it generate exhaust structures like dipolarization fronts? That's my list of what we wish we could do. I think some of those are addressable by laboratory studies, and glad to entertain any questions.
We have time for one question.
So, hey, Tom. So one of the things I'm interested in, and I think it would be valid, you know, we're always worried about calibrating these instruments. And it seems to me it would be interesting to be able to have a situation where you could model reconnection, but then also have an instrument in there that was making a measurement that would give you, I think it would give you a better idea of what an in situ measurement would be. You know, that would be something that we could do in the, I guess, near future.
Wait, are you thinking of putting a miniature instrument in a laboratory system, or?
No, but I mean, you know, or make a larger simulation vessel.
Well, you know, our sort of conventional wisdom about calibrating is that you make a delta function beam, or as close as you can to it, right? And you find the Green's function, or you find the response function of your instrument that way. I think you have to do that, but then again, you would like to be able to make the same kind of measurements in space in the lab.
Thanks. All right, our next panelist is Kristina Lynch from Dartmouth.
Good morning, everybody. My heart is in the Northern Lights, and my real laboratory is the ionosphere. But we felt the need to have a little bit of that in the lab to play around with, and that's what our elephant is. And my student tells me the elephant is an acronym, and somewhere in the lab there is a description of what elephant stands for, but mostly it's just a big silver vacuum chamber that looks like an elephant, so that's why we call it that. This one? Yep. Yeah. I wanted to, Amy asked us to talk a little about, what our goals are, and, my goals are understanding how the auroral system works. So I wanted to spend a little bit of time telling you sort of where, is there a mouse that I can, because that upper, no, it's just that the upper right panel is a movie, if you could start it. There we go, yeah. And I've started getting interested now, not so much in the drivers of the aurora, the stuff coming down that so many people have worked so hard to characterize over the last decades, that I've started wondering instead about the response of the thermal ionospheric bath to that driver. And so then you start getting into very low energies and high densities. It's a different regime. It's really messy. It's collisional. It's flowing. It's all those things that you don't really want to deal with. And so a lot of what we've been using the elephant for, I can't say that we've really gotten any answers from it, but it's certainly telling us all the things we have to look out for when we try to understand the sensors that we throw at this environment. And so our rocket this past winter had 4 little sub-payloads, about the size of 3 U CubeSats, but they're spin stabilized, that got ejected from the main payload to make a small array. And on each of these little payloads, so they're, this big, And on each little payload, we have a pair of ion RPAs. We're looking, we're in the dark in the plasma, so the payload charge is negative. So it's really hard to look at the electrons. But the ions are at least pulled towards you. They're distorted as they get pulled towards you, and they're flowing, and there's all sorts of weird things going on, but at least they reach you. And so we have an ion RPA along the spin axis and another one looking out the side, and the whole system is spinning. When you get to the idea of multiple point spacecraft, you want to have a lot of them. That's the whole point of having multiple points. And so you need to make them easy to build. So our spacecraft bus, such as it is an Arduino stack. And so we had a lot of fun making them, right, Rob? He's in the back there. He built many of these. And you do run up against the question of, can you ever answer anything? Because the better your sensors get, the more questions you have. Nevertheless, the chamber is, I think, valuable in helping you realize maybe just how dirty your system is and how careful you have to be. And so, I'm not sure what I have. Yeah, this is just an image of them deploying the payloads in the test bay, and the sort of multiplicity of parts that you have to build and keep track of. So for the suborbital missions in the lower ionosphere, you're subsonic or transonic. So interpreting an RPA in a flowing subsonic plasma is a little messy. It involves a lot of numerical integration. You have to know which way you're looking because your sensor is a little bit directional. Actually, that's part of the game. And so I think this. When I started doing this, we had this idea that you threw a sensor, like Tom was just saying, you throw a sensor in the plasma and you don't really deal with the interaction of the payload and the platform with the plasma that you're in. But as you go lower in energy and smaller in resources, to get to the thing you're trying to measure, you have to look through a lot of disturbing environment and learning a lot about what the disturbance you're creating in the environment you're trying to measure is a lot of interesting plasma physics. So this is it looks kind of like an elephant, it's got the waveguide antenna sticking out the front to be the trunk, and it's big and silver. And as Bill says, it's a derivative of the Dave Walker microwave resonant cavity from NRL. And as we've learned more about it, we've learned more and more about how complicated the plasma that's inside it is. And one of the things that has started to become a problem is if you really want to study the environment around a small payload, well, the chamber's big and the payload is small, and in principle you can put the payload in the chamber, and we would like to do that. And the payload would certainly fit in the chamber there. But the structures of the source that we've got, it's very structured. And when we started doing this, we were interested in, like, Lisa has a little sphere there, and we were looking at, what's the shape of the sheath disturbance around a conducting sphere and a floating sphere, and that kind of question. But then when you say, well, now I want to put my whole payload in there, and even though it's only 30 centimeters long, it's still, sizable on the gradient scale lengths of the plasma that's in there. And so that has been a stumbling block for us. Other things that we've done in the chamber, Bob talks about, it's a driven system, right? And so we've played around with putting an auroral beam in the chamber. So we have the microwave source to be the ambient ionospheric plasma, and then a high energy beam. And we can look at questions like, how does the combination of a electron beam against a background floating object change the float potential of the sensor? And so we've learned from experiments like that. But when I want to ask the question, I say to Rob, put the payload in the chamber and tell me what's the sheath environment around this structure. What we run up against, and I guess one of the things that I was hoping to get out of the discussions here is that in our chamber, our plasma is too inhomogeneous for that kind of a question. And I would really like to have a a different source. A source that fills, ideally fills up my chamber with a perfectly homogeneous plasma all the way across. We'll see how that goes. But one of the things that has been suggested is a plasma thruster. So there's a lot of small companies now that are building plasma thrusters for CubeSats. And if you take one of those plasma thrusters and turn it down, it's a pretty quiescent source. And so one of the things that we might try is putting one of those plasma thrusters in the chamber and playing around with that. Everything I do is done by my students, and so I can't stop without listing the bunches of them here. And I'm grateful for suggestions as to how to improve. Again, I don't think any of these are closed questions. The more you measure, the more questions you have. But I think we learn a lot as we poke around with these plasmas that we can play with in the lab. Yeah, thank you.
We have time for questions?
Of course, one of the things about the ionospheric plasmas, it's collisional. How well do you control, or is your lab even more collisional with the ionosphere?
It's probably more collisional. And again, that's something we don't have good diagnostics for. There is a plasma in there. We argue about that, about whether maybe it's... But, yeah, and, you find the textbooks are not all that helpful because the first thing they do is they assume that it's homogeneous and uncollisional and not flowing. And all of these things are not true. So, yes.
Great. Thank
Okay.
you. Okay, we're going to shift gears slightly away from plasmas here. We wanted to really have as broad of a coverage of how you do space physics in the lab. And so now we're going to hear a little bit about planetary physics. And Dan Berisford from JPL is going to be talking about simulating extraterrestrial ices in the laboratory.
Excellent. Thanks a lot for inviting me to this. Like I said, this is quite an abrupt gear shift change. I'm a technologist at JPL, which means I sort of get to pretend to be a scientist or an engineer, depending on how the situation fits, kind of like Caltech pretends it's a university or a NASA center, depending on what it wants. Usually it doesn't work out well for anybody, but I'm going to talk about a lot of experiments that are going on at JPL right now. One in particular, quite a bit of detail. And so we're really thinking about sending a lander to Europa in the not too distant future. And we don't have a good idea what the surface of Europa really looks like on a small scale. And there's a lot of overarching planetary science questions from a fundamental science and remote sensing standpoint that we're really trying to answer. This picture on the cover screen here, this is Pluto from New Horizons. And we think there's some pretty serious sublimation-driven surface features on Pluto, like ice penitentes, which I'll talk about here in a minute. So, why do we care? Again, we're thinking about lander spacecraft. Pretty important to know what the surface looks like. And we can learn a lot from doing experiments in the lab to help interpret our remote sensing data. We really want to know about planetary interiors, but maybe we can only see the surface. So really understanding the properties of the ice, thermal and mechanical properties, what can we really, how far can we go with our remote sensing data to learn about things that we can't see. So getting here again, this is over on the right here, this is the highest resolution image that we have of the surface of Europa. It's from the Galileo spacecraft, and there's 6-meter pixels. So if we blow that up to a lander scale, we really don't know what meter scale features might look like. And over here on the right, this is a picture of ice penitentes on Earth. So these things grow via a sublimation process at places on the Earth like the Andes, where you have very low humidity, and they're driven by incident solar flux. So if you have something like this on Europa, it might make landing very difficult. And so from the recent study that JPL did on the feasibility of the lander and the science return, this is an artist concept here. we also don't really know what the properties of the surface are like, and this has a pretty big effect on how you engineer your sampling tools. So is it monolithic ice, which at cryogenic temperatures is harder than concrete? Is it granular or powdery snow, which you might sink into? Are there salt crusts that form via evaporite or the sublimation version thereof? So these are some of the things that we can try to answer with lab experiments. So I'm going to focus on Europa here just because there's not time to talk about every other planet that we're interested in. So this is sort of our best understanding of what we think the interior might look like, based on a pretty limited data set of magnetometer stuff from Galileo and surface visible data from Earth and from space-based telescopes. So we have an ice crust that's maybe 10 kilometers thick. We have an ocean that's maybe 100 kilometers thick. Maybe we have some circulation regions in the ice. Maybe we have circulation underneath. Maybe we have hydrothermal vents. On the surface, we have incident sunlight and we have incident charged particles, a lot of high-energy particles, because Europa is right in the heart of Jupiter's magnetic radiation belts. And so with this surface chemistry, we can really do a lot in the lab of looking at the effect of the sunlight, what it does to the surface morphology, and we can look at the effect of these charged particles bombarding the surface and what that does to the chemistry at the surface. So enter the Europa Penitent ice experiment, or the EPICS experiment. So again, this is where we're trying to, in the lab, study the sublimation regime of these planetary ices. And of course, one of the questions we're trying to answer is, can ice penitentes exist on a world like Europa? Because the physics are very different from that of the Earth. You're in a hard vacuum, you're in a non-collisional regime a lot of times, you're in free molecular flow rather than normal fluid dynamics, and so it's sort of, there's no theory for that, for penitente formation under those conditions. So we have this little experiment here. We have two experiments. This is the static one, so it's basically just a small vacuum chamber. I was denied a scale bar by the wisdom of export control. It's about 30 centimeter diameter. And it's got a cooling jacket that we can run either liquid nitrogen or chiller fluid through and control the thermal environment. Then we shine a light through the top, and we have various optical and surface probes to see what develops from a surface morphology. And then the other part of the experiment is a full diurnal cycle test. So this can go down to full Europa thermal conditions, down to about 60 Kelvin, and can do incident solar fluxes anywhere from Europa-like to Earth-like. And so it's got a mechanical stage that sweeps back and forth, and an LED source to simulate the sun, which if anyone's interested, I can talk about the subtleties of that because there are many. And this will sort of allow us to do, this is just getting up and running. In fact, they're pumping down right now for the first long-term tests. So we do month-scale tests or more with this. So what have we seen so far? It's all pretty preliminary because these are just getting up and running. But these are the first penitentes anyone's ever seen grow in a vacuum. These are centimeter scale or half centimeter scale here. And we're sort of seeing that maybe they don't form in the free molecular flow regime. Like you actually need some sort of a fluid boundary layer in there. And so discovering this is going to, of course, drive a whole other set of experiments where we need to try to measure that fluid boundary layer on a sub-millimeter scale, which is somewhat difficult because the pressure is not well defined down there. And we've seen that ice impurities have a very strong effect, which is really important for these planetary bodies because they're full of salts and little bits of rock and other things that have a pretty strong effect on whether these things can form or not. And so long-term tests are coming up, and there's all kinds of other stuff going on at JPL. So I mentioned the particle irradiation experiment. So in our same lab, actually run by Kevin Hand, has done some pretty nice work so far on bombarding these ices. So they'll take a sample of ice, they'll add various salts or we think might be biomarkers or organic material and bombard them with charged particles, high energy electrons and ions, and sort of see what they turn into. And this sort of helps us constrain what the chemistry might be underneath the ice, and also sort of help us interpret what we see spectroscopically from far away from space. There's been quite a bit of work with salt brines and ice slurries, which really helps us sort of understand the mechanical properties of the interior of these bodies, and help us constrain sort of how thick the ocean might be and what the salinity of the ocean might be, which has pretty strong astrobiology implications. Been quite a bit of work on clathrates, which Rob will probably talk about with regards to Titan. Simulating comets, the ices on comets. Again, looking at physical properties of the ice, mechanical properties, thermal properties that haven't really been studied before in these sort of weird regimes that you don't find on the Earth. And then there's some work on tidal stressing also, where we're looking at what happens or how the planet flexes, how the ice flexes, and therefore how the planet might flex under these changing gravity conditions. So it's running short on time, and yeah, I'll take any questions.
We have a question?
I was just wondering if there's any overlap with the work that's done in the Earth's mesosphere, of seeding of particulates in the mesosphere here. Because the lab plasma community has had a lot of there's a lot of IPEL's discussion about particulate seeding in the D region in the mesosphere.
So I'm not really familiar with that. With the mesosphere in particular. So there actually is quite a bit of thought anyway. There's no funding for it yet. There were people talking about looking at exospheres on these faraway bodies, like very, very tenuous atmospheres, and their interaction with the surface. And so like changing the specific surface area of these surfaces can drastically change how the exosphere develops and or gets destroyed. But that sounds like a good thing to explore further.
All right, thank you. All right, we're going to shift gears once again, and we're going to head across the city of Los Angeles from studying the ices of Europa in Pasadena to Westwood and studying laboratory plasmas. Tripathi will be talking about the role of laboratory plasma experiments in exploring the physics of solar eruptions.
Okay, thank you. Let me begin by thanking the program committee and conveners for organizing this session. So I'm going to talk about the role of lab plasma experiments in exploring the physics of solar eruptions. And those of you who are familiar with the basic plasma science facility and the large plasma device, which is the main plasma device for conducting experiment at UCLA, this experiment was done on a slightly smaller device, which was the original LAPD, where some of the reconnection experiments were done a long time ago. So it's believed that the fundamental structure which drives the eruption of large flux ropes, such as coronal mass ejections on the sun, is arc magnetic flux ropes. And these are current carrying magnetized plasma structures, and they exist almost everywhere, not just in solar atmosphere, but also in magnetized plasma, such as in tokamaks. And here's one example of a flux rope. This is solar prominence. And of course, when you want to model such a structure in a lab, you have to make certain basic assumptions. And some of these are not just, I wouldn't say that this is a limitation of lab experiment, but rather this ongoing attempts to understand what actually a structure like this means. And when we assume that this is a flux rope, what it means that the magnetic structure of the solar prominence in this case has a net current flowing along it. And if you can take data and measure the magnetic field, you will see a twisted magnetic structure in this. So now large-scale energetic events such as flares and CMEs are triggered by impulsive eruption or instability of these arch flux rope structures. And of course, remote observations and computer models have played significant role in trying to understand what these things are. And as I believe that lab experiments can also contribute significantly, but the full potential of lab experiments is yet to be used in collaboration with the computer modelers and observations to understand what's going on. Now, being more specific, what I mean is that if you're trying to understand these structures on the sun, you don't have direct measurement of magnetic field in the solar corona further up where you need it. And even at photospheric level where you can measure these quantities, you don't have sufficient spatial or temporal resolutions. So if you can provide and understand the appropriate boundary conditions and try modeling them in lab experiments, then not just by relying on lab experiment, but in collaboration with lab experiments, computer model, and observations, we can learn a lot better, especially about the microphysics of these eruptions. Now, UCL is not the only group which is trying to understand the behavior of these arch magnetic flux ropes. Long time ago, I think in 1956, I think Bostic was the first one who tried attempting to create these structures. And initially his focus was trying to look at what causes the filamentary structure of these arch magnetic flux ropes. And even now, if you can look at the movies of things like coronal loops, you see this filamentary structure, and I don't think we completely understand what causes it. Okay. Several decades later, Paul Bell group at Caltech, they did series of experiments, and more recently their focus is on looking at the MHD physics and how in certain parameter regime can deviate and couple with kinetic aspects of it. And you can have things like flows and jets being generated. There was also a group in Germany, and I think they have stopped their experiment at this moment, but their focus was more on looking at computer models and equilibrium of these structures. And recently, the PPPL group on MRX has done very good work on looking at the equilibrium of these structures, and they have carefully investigated things like torus instability and kink instability, and what are the limitations when you want to apply those conditions to the solar case. Now, coming back to the actual situation, of course, this is my perspective, and this can be probably the simplest possible schematic for solar eruptions. So what you are seeing here is, in this panel, is the region of positive magnetic field and negative magnetic field, which is red, and these two regions marked with plus and minus, separated by this polarity inversion line. And you see this arch magnetic flux rope structure, which has, of course, magnetic field and current flowing along it. And this structure is held in a stable position by these trapping magnetic field lines. And of course, these field lines are not just vacuum field lines. There's a low density plasma content in this. And of course, there may be multiple scenarios where there are different kind of magnetic forces which are trying to destabilize this structure. And you can group them in like inward force and outward magnetic forces. And whenever you see there's an outward force overwhelming the inward force, you can see the structure taking off, and then that should lead to the eruption. Okay? Now, in my view, it appears unlikely that there will be universal mechanism that can explain all possible eruptions on the sun. Okay? So when we want to model these structures, you need to precisely know what boundary conditions you have, and I think that part is still being debated in solar physics community. What kind of exact boundary conditions there are, how the flux is building up, where it's being built up in photosphere corona. But when we want to model in a UCL experiment, there are two key observations. The first one we said is that these structures are stable for many, many alpha transit times before their sudden eruption. And when they erupt, they can generate even larger flux rope structures that may form, such as coronal mass ejection on the sun. So this is the experimental setup here. And to do it, of course, you have to adopt like modular. So these are like modular plasma sources. So this is the inner view of the vacuum chamber. And on the left side, you see this bright hot cat cathode lab-6 source. On the right side, you see another smaller lab-6 source. And right above this small lab-6 source, hot source, you see another electrode. So these two electrodes, they form the foot point of your flux rope. So here's the vacuum magnetic field linking these 2 foot points in the experiment. Okay. And using this plasma source, this modular plasma source, we can produce a plasma along these field lines, and we can also drive current. And when you raise the current above certain limit, then you see this outward force, which is called hoof force, and that force leads to the eruption. So basically, you see this structure starts evolving. At the same time, you also have background magnetic field, and there's also plasma. And we have flexibility in changing the relative density, relative angle between magnetic fields, and look at different scenarios where the structure can erupt. Now, since we have background plasma with variable magnetic field, we have flexibility in wave studies. You can look into things like fast wave in this experiment. And at the same time, this experiment works in the LAPD mode. What it means that you create this structure every 2 seconds, and the whole system is automated. So if you wait 2 days, you may create almost like 10,000 eruptions. Of course, every single shot, you see this complex dynamics. Okay? It's not like steady state. But then it's very reproducible. And since it's reproducible, you can take your small probe, or you can consider them like a mini satellites, and you can move them from one point to one point with a millimeter resolution. And by relying on this technique, you generate 3D data of almost all useful plasma parameters you can think of, such as plasma density, temperature, magnetic field, and even your energetic particle distribution. You can capture it in 3D. And I think that will be very useful if you want to compare with computer models. Now, just to give you some of the main results, we have looked at the eruption in several configurations. Okay? And one case where we had like a fast injection of magnetic flux, another case where we had slow buildup of magnetic flux. And it doesn't matter how we build up that flux, but once the structure erupts, it erupts on a much faster time scale, and there are certain features that are always there, such as ejection of much longer flux rope. Okay? And if you are interested in more details, you can come to my poster later in the afternoon. Okay? And how much time I have? Okay. Okay, so I'll just show you one movie before showing the last slide here. So this is a picture of the one case where you can see a small flux rope, arch flux rope forming. It's not playing, I guess. And then you see it erupt, and at some point it will detach from primary structure. And of course what you're seeing looks like a blob, but this is extended structure. And you see this large flux rope actually coming out the board of this plane that you're seeing here. So you start with a small flux rope and generate much larger flux rope structure. And it's very clear when you look at magnetic field measurements. If you move far away, like meter on one side, half meter other side, and you can see this azimuthal flux rope, azimuthal magnetic field structure. And if you run a movie, you can see it going back and forth, which indicates that this is a large flux rope. And let me skip this and go to the final slide. Just an advertisement that, as you know, that basic plasma science facility is a user facility, and we devote almost 50% time and collaborating with the external group and letting them run the experiment on LAPD. And there's particular focus on space physics relevant experiments on LAPD. And currently the deadline for white paper submission is December 22nd, 2017, and this will allocate time for experiments in the next year. And if you're interested, you can contact Troy Carter or talk to me in this meeting. Thank you.
We're going to have to move on to the next one, so if you have any questions, just hold it for the discussion. Thank you.
All right. So our next speaker, returning to space, is Justin Kasper, who will be speaking of the coupling between non-thermal plasmas and magnetic fields in space, in situ and remote observations with Parker Solar Probe and Sunrise.
Thank you. Morning, everyone. I'll try to be succinct here. I wanted to give two examples of experiments in space where I think laboratory experiments could be really useful. So what I'm interested in is like heating of the solar corona, acceleration of material in the corona to the supersonic solar wind, energization of particles via flares or shocks within that corona or solar wind. One way we're trying to understand all of that is the Parker Solar Probe mission, which is launching in July of next year. Overall, probe's objectives are to determine the structure and dynamics of the sun's coronal magnetic field, understand how the solar corona and solar wind are heated and accelerated, and determine what mechanisms accelerate and transport energetic particles. There's an artist sketch of probe, basically gets to within 10 RS of the sun after about 7 Venus gravity assists spread over 5 years. So walking closer and closer in. Just 3 months after launch, we'll have our first encounter at 35 solar radii, which is 1/7 of an AU. So it'll already be a lot closer than anyone's ever gotten before. And the spacecraft is basically a big heat shield with a whole bunch of really good particle and plasma and electromagnetic field and imaging instruments, most in the shadow, some peering around. So we're very excited about the data sets we're going to get. We think they're very comprehensive. Instruments are very well calibrated. And we've divided the sort of objectives of the spacecraft into 3 kind of lower categories. We want to trace the flow of energy that heats and accelerates the corona and the wind. So, how do you get from, turbulence to hotter plasma as a function of distance from the sun? And what are the rates at which that energy flows? We want to try to relate the structures we see to structures back in the corona, and we want to see what's accelerating energetic particles. Just to give you a flavor of the kind of data that we produce, this is stitching together existing spectroscopic data on the left and in situ data on the right for ion and electron temperatures versus distance from the sun. Yeah, and this kind of illustrates the coronal heating problem. So the black line is kind of a model of a single fluid temperature. You start out at the surface of the sun at 5,000-6,000 degrees Kelvin. Within the transition region of 100 kilometers or so, the temperature jumps 100,000 degrees. That's a problem. But then over the course of the next few solar radii, the plasma is heated up to millions of degrees. Minor ions are heated mass proportionally up to hundreds of millions of degrees. And even when we get further away, heating continues to happen. We don't know how to connect those lines because we don't have any data. Probe's going to go fill that region in and hopefully have electromagnetic field measurements and thermal plasma measurements at the same time to really understand unambiguously what are the mechanisms responsible for that heating. So what will the coronal plasma look like? There's a million things we could talk about. Let me just throw up two thoughts we have. On the left, this is a simulation in 2 panels. The panel on the left is outward-going Alfvén waves, just being launched randomly from the surface of the sun. They kind of tilt to the right. We're looking at height versus time because they're propagating outward. And on the right of that figure on the left is sort of the fraction of reflected wave power traveling back towards the sun. So the Alfvén point in this model is at 14 or so solar radii, and we think that if we get below the Alfvén point, you'll see this mix of inward and outward propagating waves. Maybe that's what's superheating the corona. We'd love to have whatever insights we can into how energy cascades and heating and dissipation rates change when you have that counter-propagating reflected waves. We'd like to know what really is reflecting the waves. Is it really just the Alfvén point and talking about wave speeds, or is there some other reflection process going on? On the right, this is just a plot of proton temperature anisotropy on the y-axis versus plasma beta collected at 1 AU. What you can see is for beta greater than 1, the anisotropy of the plasma is limited. T-perp greater than parallel on the top, it's limited by the mirror and the cyclotron instabilities. Below, it's limited by the fire hose instability. Is any of this going to be important when we're close to the sun, when we're in a low beta plasma? We think the corona, people say beta is 10 to the -2 or so, so maybe we're so far over to the left on this plot, we'll see ridiculous temperature anisotropies all over the place, or maybe other factors are going to kick in. So when I just think about laboratory experiments that might complement a mission like Solar Probe, I'm just going to give you a couple examples. Probe is unfortunately one spacecraft, so we don't have much sense of the 2-dimensional or 3-dimensional structure of the turbulence or the fluctuations we're going to observe. So it'd be wonderful to have laboratory experiments operating in this lower beta, higher temperature regime that might help guide, how do we interpret our 1-dimensional scans in terms of 2- or 3-dimensional structure. We assume things like turbulence are going to just change when we're in this lower beta plasma. I mean, we have snippets of low beta plasma at 1 AU, but when we're close to the sun, we think low beta will be very common. So just, what are the more capable waves for dissipation at those lower beta conditions? We have a wave-particle correlator on the spacecraft, so we can combine the arrival times of particles in the thermal plasma with the electric and magnetic field and look at phase and wave correlations at timescales of like hundreds of nanoseconds. How do we make use of that to try to distinguish between different types of wave-particle scattering techniques? I mean, look at Landau damping demonstrated in the laboratory. Are there other dissipation demonstrations you can do, and then tell us what the wave-particle correlation signatures are like that we could take advantage of? So that's happening. It's launching in a few months. I just wanted to mention another mission I'm working on that was just selected for a concept study through what's called Explorer missions. And this is Sunrise, the Sun Radio Interferometer Space Experiment. This is a project I'm working on with JPL, and what we want to do is try to get some insights into how energetic particles are created close to the sun and then how they travel away from the sun. And the idea is we build a whole bunch of small spacecraft, each about yay big. We stick them in the back of a communications satellite, which launches, goes up into geosynchronous orbit, and actually goes a little bit past geosync for us, shoots us off into a constellation. So we have basically a cloud of small satellites about 10 kilometers across. Each satellite then deploys a pair of crossed 5-meter dipole antennas. So basically you're able to create synthetically, by combining the data from them, a digitally steerable 10-kilometer diameter low-frequency radio aperture that runs from about 100 kilohertz to 20 megahertz, frequencies that you can't really image from below Earth's ionosphere. There's a ton you could do with that. We've never been able to do low-frequency imaging from space before. Our primary focus is two things. We want to look at coherent radio emission, which are called, not very excitingly, type 2 and type 3 bursts from the sun. We want to use those to study very specific things. So just as a reminder, on the left, a little schematic of the sun, a solar flares just happened, a beam of like nearly relativistic electrons has escaped. They're moving at, I don't know, 1/10 the speed of light, and they're going to shoot out along a magnetic field line. So that electron beam moving along the field is unstable, generates Langmuir waves. Langmuir waves convert into radio waves at the local plasma frequency, and it's harmonic. We, way far away from the sun, pick up that emission super bright, effective brightness temperatures of like 10 to the 12 Kelvin sometimes, as the little packet of electrons moves away from the sun. And in the middle plot here, you can actually see the ones labeled A, or it's just a sequence of these type 3 bursts. So bam, 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 little packets of electrons coming away, emitting and dropping in frequency very quickly as they descend out. On the right, you can see this type 2 radio burst. It descends in frequency much more slowly, and the emission it comes and goes. It's more intermittent. What that seems to be is coronal mass ejection is erupted from the sun. There's a shock wave. Somewhere around that CME, electrons are being accelerated, and then through a similar process, they're generating this coherent radio emission. And we're watching the frequency drop at a much lower rate because the shock wave is not moving at the speed of light. It's moving at, boring 1,000, 2,000 kilometers per second. So what we want to do with Sunrise is twofold. We want to be able to look at those shock-associated electron bursts and image them and just say, where relative to the shock are these electrons being accelerated? Turns out every major energetic particle event is preceded usually by about 10 minutes by the onset of this coherent radio emission. The other thing we want to do is just trace those type 3 bursts, and basically in 3 dimensions, because the frequency relates to the density. Density falls off as 1 over r squared. We can image the emission. Basically, every type 3 burst, you make a 3D measurement of a magnetic field line. So for Sunrise, what are some examples of things we'd love to see? We don't have a great feel for the intensity and duration of the emission at the fundamental and harmonic of the plasma frequency as a function of things like the electron beam properties, the turbulence. Right now, like most of what the community does is they plot like the peak frequency versus time, and you fit a line to it, but you don't do anything with the intensity, you don't do anything with the duration. So experiments that tried like just different levels of beams and what kind of
intensity wave you could excite would be fascinating for us. All right, I'm going to leave it there.
All right. Thanks. All right, and we're going, oh, you can go ahead.
Okay, Rob? Okay, so once again, we're going to move away from the sun and off to a distant moon. And we have Rob Hodyss from JPL speaking about Titan's lakes in a beaker.
All right, so like Dan, I'm going to talk mostly about surface properties on a moon in the outer solar system, but we're moving further out into the solar system now from Europa to Titan. So Titan is unique in the solar system in that it has a complicated organic cycle that occurs between the atmosphere and the surface. Titan's atmosphere is mostly nitrogen with a few % of methane. At the surface, the pressure is 1.5 bar, but the temperature is 90-something Kelvin. So the density of Titan's atmosphere at the surface is actually about 4 times what it is in this room. Photochemistry in the upper atmosphere produces a wide variety of organics, which eventually condense and then rain down onto the surface. And so in a lot of ways, Titan is like Earth. Titan has clouds, it has rain, except the rain is liquid methane or liquid ethane. There's rivers, there are lakes and seas, rivers that transport material across the surface. There are extensive dune fields across the equatorial regions. There are evaporite deposits like you see out in the western United States. But on Titan, all of this is made out of organics, organic molecules, not minerals and salts like you expect, like you see on the Earth. And so the goal of the research that we do is to try to understand these individual processes, to try to understand how things can be transported, how things can be dissolved, how materials are reprecipitated back onto the surface. And so I'm going to just give you one example focusing on 2 molecules that are expected to be on Titan's surface. One is ethane, which is a small hydrocarbon, which is liquid under Titan surface conditions and makes up part of the volume of the lakes. And the other is benzene, which is another small hydrocarbon, but is solid under Titan conditions. And so one of the really basic questions that you ask, on Earth, the seas are full of salt. On Titan, are the lakes and seas full of something else? And so our first question that we really wanted to answer is, with those two molecules, is what's the solubility of benzene in liquid ethane? And this is a very basic and simple chemistry experiment. You take your liquid, you add your solid, and keep dissolving in it until no more dissolves, and then you measure the concentration in the liquid. And so this is what we do with Titan-type materials. We have essentially a beaker that is liquid nitrogen cooled and resistively heated to get us to 92 Kelvin, the temperature of the lakes on Titan, and we measure the solubility of benzene using ultraviolet spectroscopy. So in the system, you cool the system, condense in liquid ethane, add solid benzene, wait a while, periodically measuring the concentration using ultraviolet spectroscopy. There's some filter tube to get rid of solids, and you eventually reach saturation, which is the number you're looking for. So the first thing that you notice is that dissolution is fast, even at 94 Kelvin. This is, a little surprising. You can think of when you dissolve sugar in coffee, it dissolves really fast, but if you try to dissolve sugar in cold lemonade, it dissolves really slow. You'd expect at 94 Kelvin, dissolution rates would be really, really slow. They're not that slow. We reach saturation in a couple hours. What's sort of more expected is the solubility. Benzene itself has a saturation concentration of only about 18.5 milligrams per liter, so that's not very soluble. It's poorly soluble is what you'd call it. We've measured a number of other molecules as well, but like naphthalene and biphenyl, other organics, and we're continuing these sorts of measurements. So what can you do with this kind of information? So we know the solubility. You can look at what you think is happening in the lakes. That's a picture in the upper right there of Ontario Lacus, one of the lakes in the southern hemisphere. If you assume a depth, you know the surface area, you can calculate a volume of the lake. From atmospheric photochemistry models, you can get a rate for the atmospheric flux of benzene to the surface, which is about 10 to the 6 molecules per centimeter squared per second. And so you can calculate that you reach saturation in the lake at about 4.5 million years. The lakes on Titan are almost certainly older than that. And so we can say that the lake is probably saturated in benzene, and in fact there's probably a benzene sludge at the bottom of it. There's probably a lot of other sludgy things at the bottom of it too, but there's at least a benzene sludge at the bottom of that lake. So, we wanted to sort of more closely understand the relationship between benzene and ethane, and so another experiment that we can do is just to microscopically look at what happens when you put these two materials together. So on the left is an image using a Raman microscope, actually, of solid benzene at 94 Kelvin. You can see the scale bar there is about 100 microns. So they're small crystals of solid benzene. The image on the right is after we've poured liquid ethane onto those crystals and waited a little while. And what you see immediately is that it's recrystallized. The crystals have gotten a lot smaller. So something has happened. And this is odd. You wouldn't really expect benzene and ethane, they're both nonpolar molecules, to do anything. But they've done something. Like I said, this is also the microscope is also attached to a Raman spectrometer. And so we can get Raman spectra of the new crystals that have formed. And so Raman spectroscopy probes vibrational interactions. And so you can understand from it what parts of the molecules are interacting with each other. So the bottom red trace is pure benzene. The middle black trace is a mixture of benzene and ethane prior to when that recrystallization happened. And the blue is after the recrystallization has happened. And what you see is the emergence of this new peak here and the shift in these peaks, which are benzene vibrational modes, indicates that there's a very specific interaction between the benzene molecule and the ethane molecule. And so what we actually think is happening here is that we're getting the formation of a co-crystalline compound. So Raman is great for seeing that something is happening, but it's not great for getting you really good structures. It tells you about interactions, but not overall structure. So we were able to go to the Australian synchrotron and do X-ray powder diffraction on the sample, on a sample of benzene and ethane. So it's encased in a capillary there, and you can see that's solid benzene there, and you can sort of see a little bit of a meniscus there where the droplet of liquid ethane is in contact. You can see the bottom blue powder pattern of pure benzene is very different from the XRD pattern that you get after you've let these two materials interact. From the XRD pattern, it's possible to actually derive the structure that you're seeing. And so this is a single unit cell of this structure. This is a benzene-ethane co-crystal. So a co-crystal is a crystalline material made of two different molecular components in a set stoichiometry. And so this is 3-to-1 benzene-ethane. And so it's sort of hard to see these sorts of things, but what you see is you see 6 benzene molecules surrounding the ethane molecules. And the ethane molecules are actually in a sort of a channel formed by those benzene molecules. We think that co-crystalline compounds like this are probably common on the surface of Titan and may dominate some of the geology that you see on the surface. So I'll leave with just a few final thoughts. We know almost nothing about what the chemical composition of the surface of Titan is. The Cassini mission sort of revolutionized our understanding of what we see, but we still don't have much true knowledge of what the real chemical composition is. And with Cassini now over, laboratory experiments are the only way that we have to explore this kind of chemistry. And this, for the development of future missions, it's crucial to understand both these material properties and the chemical properties of these of the surface so that we can do proper design of sampling systems, sample handling systems, and the landing systems. And I'll leave it at that. Thank you.
We have time for one quick question.
Is there a discussion to follow-up missions to Cassini, or are you guys
There's-
at this point like just stuck doing lab experiments?
There's lots of concepts for Titan in situ missions. Titan's a great place to go because you have so many different environments. There's lots of interesting concepts. Because the atmosphere is thick, you can fly. There are concepts for planes, and in fact, there is a concept in the latest New Frontiers call for a sort of a quadcopter kind of idea that would fly around Titan. The lakes also give you the opportunity to have things like boats that float around, and there are even concepts for submersibles. So there's lots of concepts, but we haven't gotten back there yet. So.
Great, thank you. Well, first, I'd like to really thank all of our speakers. I think you've done a really great job at addressing the main goals of this session. And now, for the next 30 minutes until 10, or slightly less than 30, we're going to have a little bit of a Q&A panel discussion. We're going to take any questions the audience have. I imagine you probably have a number of things. You can address it to particular panelists, or just to the panel in general. And please, all of you, even if a question is addressed to another person, if you feel like you have something to contribute on that, please, do chime in. Raise your hand so we'll know we'll get to you. There are 4 microphones, so you'll have to sort of share there. But let me open up the discussion to the floor. If anybody has any questions, please raise your hands. Lee Jin?
Yeah, that's an interesting set of experiments that we could tackle. That could be a wide variety of diagnostics applied to that. So everything from simple Langmuir probe, electrostatic probe measurements of the density perturbation, resolve versus time, to emissive probe measurements, looking at the potentials before and after shock passage, even some non-invasive diagnostics, possibly LIF type measurements, potentially to look at non-perturbative ways of looking at this. Energy analyzer measurements to look at differences in the particle energization before and after passage of the shock, and innovative new diagnostics too that we're looking to implement, where we can time resolve fluctuations in the electron distribution function. Perhaps some of the others, have ideas for diagnostic techniques.
Any other panelists have any comments on that?
Maybe I can comment on this. So probably you're aware that even on large plasma device, there's collisionless shock experiment. And we use multiple diagnostics, as Bill pointed out. And actually one area where we can make a lot more progress, and that's where I think some of the space measurements are a lot better, is measuring the particle distribution function. Mm-hmm. Because when you have structure like this being generated, like collisionless shock, so you don't have very uniform magnetic field or plasma density. So you really need 3D measurement of particle distribution function. And that's one area where we can improve a lot more on this.
So I'll also mention, of course, our panelists are a good representation of some of the lab facilities around the country, but they don't represent everyone. There are other experimental facilities around the country, in particular the plasma liner experiment at Los Alamos National Laboratory, where they actually have a number of plasma guns that can be fired directly towards each other, so you get these magnetized plasmas impacting on each other, and they've been able to very successfully model collisional shocks, and they are pushing to the high energy densities necessary to model collisionless shocks. So there are other facilities that exist and are under development and constant refinement and improvement that can address some of those same questions. Masaki. Yeah.
Yes, my name is Masaki Yamada, and I have been co-organizing ITER's meeting for the past 20 years, and I appreciate you have organized this collaborative session so that we can talk between, we can have conversations between the lab physicists and the space physicists. And indeed, as Tom Moore mentioned, and personally I enjoy the conversation with the MMS group. In particular, as the slides show, that we MRX as Princeton people have been working on the electron diffusion region. We identified about 10 years ago, but then we found that recently, 2014, I think we published the data physics, that so-called J.E, energy deposition to the electron, J.E, surge up around the electron diffusion. And since then, I have been talking with the Jim Birch, you should find this, and so on. And finally, in the first science paper, it came out. And we are so, in a sense, proud of bragging, in a sense, and we are so happy to see that, confirmation or verification from space time. And we do other way around too, we observe. And this type of collaboration has been very productive. So I would like to invite you all to this IPAS meeting, which will be held in Tokyo, University of Tokyo, in a collaboration with the Solar Parker Pro, the workshop. So we'll have a nice collaborative meeting. So we invite you all.
Yeah, so that IPELS meeting, it's the interrelationship of plasma experiments in laboratories in space. That's this IPELS meeting. It will be held in June 2019, I believe, in Tokyo. September, okay, in Tokyo, Japan. So that's upcoming. That's a great environment for, yeah, they're still finalizing things. It's a great environment for these kinds of interactions. We had another question there.
Yes, so I'm wondering if panelists could comment on laboratory plasma physics as like a transformative medium to bridging the gap between some of our different fields, whether it's reconnection, solar regions, or magnetosphere, or maybe there's connections between plasma physics and the mesosphere and astrobiology, or all kinds of like big open questions. And is all that discussion happening at places like IPELS, or how can we make it happen more?
Okay, does any panelists have any responses there?
Well,
yes.
I'll say that, for instance, Alfvén waves are a fundamental phenomena that are ubiquitous in plasmas all over the place. My interest originally was sort of auroral kinds of things, but happen in the sun, happen in the solar wind. And so what I would say is in what you can do in a laboratory is often study the detailed plasma physics of how things behave, which then informs all these different fields. And so that is one of the kinds of things that you would see at the IPELS meeting, is that people will talk about Alfvén waves in near the surface of the sun and the solar wind, auroral kinds of situations. But often what we're trying to get at is, do we really understand the details of how the plasma physics itself works? And so in that sense, I think that is one of the kinds of things that the laboratory and space collaboration brings, is finding often many phenomena that are in many places, such as reconnection is another one that happens in various places in the magnetosphere and the sun as well. And then by looking at these different regions and seeing what you can do in a laboratory, you're pulling things together so you kind of understand the universality of some of these processes.
Justin, did you have something to add?
Well, I was going to, maybe this is just too jokey. My first thought was, the number of times I've thought I'm figuring out something new, in the corona, and then I learned it's been seen in the ionosphere for 30 years, and why didn't I just read the literature? So the thought that I'd go to a third group to get me to read the papers I should have read anyway, I don't know if that'll work. But I'll tell you, I found it very refreshing going to a laboratory plasma meeting. The terminology is often different, the techniques are different, and it's a little jarring. And I find that makes me actually think a little bit more about what's going on, and so I've learned a lot from going to those meetings. You know, I always feel like as a space experimentalist, surely there's something interesting I can come up with to do in a lab plasma. And that's another aspect of this. Like, we build all these particle sensors. Is there any way we could be helping integrate those into lab experiments? You know, so far, it seems like often the dimensions are just so different that it's more a matter of comparing notes on similar plasmas and processes, and not necessarily that we can make use of the same experimental techniques.
I'll add a little something to that, actually, is that Carrie Black at NSF just asked me, she's like, you know, why is it that people are talking about this so much more now? You know, there have been efforts of using lab experiments to try to understand space physics phenomena for a number of years, I mean, decades even in some cases, but I think it's really gaining a lot of steam, and there's actually a pretty easy to understand reason why, which is that lab experiments in the past have had smaller energy densities, smaller vacuum chambers, and they really can only access the smaller scale physics, the physics that might be below the ion scale, something like that. They don't have strong enough magnetic fields in order to have a small ion Larmor radius relative to your plasma size. But over the last, you know, sort of decade and now, we have much bigger facilities, higher energy densities, so the laboratory plasmas can push from sort of these kinetic length scales up into more the fluid kind of MHD type of length scales to study. And at the same time, spacecraft instrumentation is going to much higher cadence, and their ability to sample the plasma physics is now pushing from the larger fluid scales of MHD down into the kinetic length scale. So there really is a true overlap of the same plasma regimes that now, today, can actually be explored both in space and in the laboratory. And I think that's really what is driving, and what I think will drive especially a lot of progress in this area, and part of what drove this whole effort to have this panel and to have the workshop that Amy talked about back in April last year, or earlier this year. I just wanted to make that comment because it's something that I think it's sort of obvious when you think about it, but a lot of people really haven't thought about it in those terms. Kristina.
Yeah, I just wanted to say it always surprises me at plasma meetings at how many connections I have to industrial plasma physics. The lower ionosphere is, like I said, dirty and inhomogeneous and collisional and flowing. And, you know, the chip makers have been dealing with this for decades, and they know a lot that it's interesting to try to learn from them. So.
Right. Do we have other questions from the audience? There, yes.
Thank you. I'd like to thank Cameron and Dr. House for your work on this, especially here in I just wanted to give a real quick shout out to the Wisconsin Plasma Physics Laboratory, which is a new user facility that's accepting proposals for experiments just of this type, or any other type. And we'd love to hear your proposals if there are any. If you don't know, it's a combination of a reverse field Lynch experiment, and also 3-meter spherical vacuum vessel that can confine plasmas without applying significant magnetic fields to them, so you can apply whatever field you'd like to. We've done so many of these types of experiments. We've done reconnection, we've done shocks, we've put a giant spinning dipole in there and tried to make a Harper spiral. We've done dynamo flows, and we're open to the business, and we'd love to hear your proposals if there are any.
Thank you. We had another question? Yes.
I really enjoyed the comments about how sometimes it's difficult to untangle what you're seeing because the spacecraft is charged and spinning. And I've definitely worked with that with linear probe experiments and such. And if there had been consideration of how to model sort of the difficulties of the measurement device itself in the plasma chamber, whether it's spacecraft charging or the movement of the probe.
Okay.
I guess I'd want to have Arrow answer that one. You want to speak to that, Earle?
With respect to language, right? Yeah, it's one of the things about these fundamental instruments of the linear approach that have been around for almost a century is that the theory assumes a lot of things, like you connect long cylinders and spheres and so on. And it's very hard, not just in a lab, even in space, to create those idealistic instruments. I don't think that the intent should then be to create an instrument which will conform exactly to the theory, rather to figure out how the theory adjusts so we can now understand the instrument better. And there are efforts on those lines.
So we had another question there, yes?
I have just a comment.
Okay.
I see the Lab Plasma experiment is very important because their first hand was made in the situation. And however, the limitation of Lab Plasma study is very important to know. How can we know if our device big enough, good enough, date the situation? That's very deep physics question. So the theoretical understanding is number one. It's actually the space plasma right now is in halfway. It's not just like a textbook. There's something we need to develop because we want to understand is what we want to understand is high energy particle acceleration, for example. You cannot, if you don't know theory, you put the lab experiment, you waste your time. Yeah, because lab plasma different with space plasma. One important thing is the space plasma is far from thermal equilibrium and very inhomogeneous. Even the theory even developed that stage. We talk about plasma physics. Plasma is quasi-neutral, but what we deal with is charge separation in the cosmic plasma. So I gave the main point is to understand the theory, to develop the theory is fundamentally important. Amanda with you gave proposal to NASA on ISI saying they use $1 million to study reconnection. Where reconnection happens is far from thermal equilibrium. It's a dynamical state. It's some physics we are undeveloped.
Okay. Thank you for that comment. So there is a place for theorists too, so do not despair. Okay, I think that's
we do
important.
let you near the lab every now and then, Greg.
Every once in a while. Yeah, I'm a theorist, so you know.
But it's a point well taken, actually, in the following sense, that many laboratory plasmas are collisional and most space plasmas are not. So one of the things you do have to do is develop your theory to a point that you understand exactly how collisions are coming in, so you can sort of extract that away and say, now this is how it applies to a space plasma. But then I put it in to get agreement between the lab, and so I would agree. I mean, you know, just doing experiments is, you know, it's nice and fun, but you have to analyze them and understand what they're telling you.
I'll wait for a second, Masaki. We have two other questions. You first?
I understand that the emphasis of this discussion is on laboratory experiments and in situ experiments, but I think that the problem is a four-legged creature, maybe like an elephant. It is the lab, the in situ measurements or exploration theory, certainly, and simulations. Simulations are slightly different from theory, and it's by combining all these aspects, these approaches, that we're going to get a really good understanding, because it has been, I've heard the word, I think, or the mention of simulations or maybe theory from the panelists, and it was also mentioned that the conditions are never exactly what is assumed in theory, that the plasma is magnetized, it's drifting, it's inhomogeneous, and there are things happening in space that are maybe difficult to reproduce in the lab. Photoionization is not so difficult as well. But with simulations, it is possible. It's not easy, but it's possible to account for this, and it has been done in selected cases where simulations have been applied to lab experiments, accounting for fairly realistic conditions.
Right. Excellent. We didn't mean to leave simulators out either. So the elephant has 4 legs: theory, simulations, experiments, and spacecraft observations. Just remember, 3-legged elephants don't move very fast. So
it also has a tail and a trunk.
Perhaps 4-legged. So, you know, they say that no one believes the model except for the person that did it. Everybody believes the experiment except for the person that did it. So as unless you can tie all 4 of those pieces together, the modeling, the theory, the experiment, and the observation, if you tie all 4 of those together, then you really can say something definitive that you understand a new physical process. If you can't, then maybe you don't really know anything. You can do 1 million experiments that don't really tell you much unless you've really thought about the limitations of the experiment. I think it's universally true across all fields. I think.
Yeah, Bill?
Yeah, I'd like to suggest that perhaps it's a 5-legged elephant. There's one aspect that we haven't mentioned, and that's active experiments such as trying to perturb the ionosphere with heaters like HARP, Arecibo, places like that. You can do controlled experiments from the ground to perturb the ionosphere and see how it responds. And that's a very interesting aspect as well that should be folded in with all of this.
You know, in that regard, I want to point out a kind of an experiment of opportunity that got done with the space shuttle system when the plasma diagnostic probe flew around it back in the 80s. When there was a gas release from the shuttle, which happens for various reasons, there was ion heating observed in the environment around the shuttle. That's never really been chased down fully, I don't think, as far as what physics was operative. Well, maybe there's some way to do similar things.
Paul Bernhardt did a lot of experiments with dedicated shuttle burns and coordinated with observations, many kilometers away with various conjunctions of satellites to look at wave propagation. There's a whole bunch of literature. Yep.
I also wanted to comment that simulation is very useful. In fact, the wave-wave coupling example I showed when I was speaking actually came from Greg Howes, who said, this is what you need to do with your laboratory experiment to get what we've been trying to see for quite a long time. So in that sense, the simulation suggested what we did. We set up the experiment that way, and amazingly enough, the things agreed pretty darn well. So it definitely, all these pieces have to come together.
There was another question over here. Yeah.
Yeah, that's an excellent question, because when you start to look at the parameter space of what you might find on Europa, when you start looking at different temperatures, different pressures, different amounts of impurities, different types of impurities, pretty soon your parameter space grows to an impossible amount of experiments that you have to do. So what we're trying to do is so we take observational data of the surface, so we have some idea of what types of impurities we might find there. And then we try to run experiments that can tell us trends. For instance, if we look at a salt like magnesium sulfate, say, we start with saturated solution. We make ice from that. We see no penitentes, then we go to a very, very dilute solution. If we see no penitentes, then maybe we throw that out and we go to the next one. If we start to see interesting surface morphologies happen, not necessarily penitentes, there might be other things that we don't know about, then we start to chop up that parameter space and make more experiments there. But it is a tough problem, because we're never going to be able to do enough experiments. And so I think the best that we can do is to try to figure out, the most promising ones that are going to tell us something useful for a lander, and then develop trends and try to extrapolate from there.
So, sort of from our perspective, what we tend to do is avoid the issue entirely. The Titan organic chemistry is so unknown that we can focus on really basic questions like, does it form or doesn't it? What is the crystal structure? Where the impurities don't really matter all that much. So we just avoid it.
So I think we have time for just two more questions. Jimmy?
So to follow up on some of the mentioning of simulations and theory, I actually have a bit of a sociological question for the panel, which is that when you guys find something interesting that hasn't been seen before, do you feel that there's actually a short turnaround between your discovery in the lab and actual computational support to try and provide a theory for that? If not, why, do you think that is actually more the fault of the computational side of things, like there's just a communication disconnect? Or if your experiences are different across the panel, what are those experiences like, and what do you think maybe we can be doing so that, when you guys see something exciting and new, there actually is a lot of movement quickly to provide theory and simulation support?
In my experience, it's often a funding disconnect.
Our experience at NRL has been, of course, maybe it's because it's a function of being at NRL where we have theorists and experimentalists working together daily, is we are in constant contact, and so these things are happening in real time where we see something in the lab and can get our theory and computational support immediately. So we're spoiled in that sense.
I'd say that, my experience has been that it can sometimes take time, partly because coming from the space community, most of the theorists that I know are, we're always with collisional kinds of things. And so suddenly, one of the problems that held us up for a while in understanding what we were seeing is, how do we bring collisions in correctly? And it turned out, actually, it was not that difficult a thing to do, but it's just not something kind of in my training and all the experiment I'd done, I'd ever really had to deal with before. And so I talked to a few people, but many people in the space community have never dealt with collisionality either. And so it's kind of discovering people, and you talk to people at the IPELS meetings and drag them aside, say, what do you think about this? And so sometimes it's very quick, and sometimes you find the right connection and away you go, or other times it can just take asking questions of a number of people till you finally figure out where's the right place to go.
Yeah. All right, I think we have time for just one last question. Masaki's been waiting for a while, so please.
When we try to compare the laboratory data and the space data or phenomena, if we just try to simulate the phenomena itself, usually so difficult, you rather concentrate on the process, basic process, then you compare. So through that comparison, the most important part is simulation. Numerical simulation of the lab. So this, about 10 years ago, when we tried to build the center, Bob Rosner and I had a long discussion, we came to this conclusion. The fundamental process is easier to do, but if you try to do the whole phenomena like a solar flare, that's much harder. So we should concentrate on specific geophysics process. That will bring in the theories and bring in the numerical simulation. That is, I think, the key.
That's good, yeah. So focusing on really those fundamental processes. So we're out of questions. There were a few more hands, and I'm sorry that we didn't have a chance to get to absolutely everybody, but that's good. That means there was more to talk about. I want to really thank our panelists for doing a phenomenally good job of really addressing the topic and having some great comments to make. Thank you very much. And I appreciate all of you here. I hope there's much more to talk about, the interrelation between lab experiments and space physics. Thank you.